So our next example is actually a current source, this time supplying a parallel combination of a resistance in parallel with a capacitance. So for capacitances this time, similar to that of your inductance, cut the story short, if initial values for the voltage across the capacitance is non-existent or zero, just as how it is for the second example, because if you look at the figure, it's actually derived from an open circuit. So it started from an open circuit. So it's very obvious that during the open circuit condition, the voltage across the capacitance is zero. So there is no initial value. And if you're going to recall the impedance model of your capacitance, again, same as that of the inductance, you have two types. So the first one is it can be modeled using a voltage source, and the other one can be modeled using a current source, both of which involve a value of V of 0 in them. So if V of 0 is 0, then the voltage of the voltage source is 0, which means it's a short circuit. Or the current of the current source is also 0, which means it's an open circuit. So if there is no initial value, the impedance model of your capacitance is simply a single branch with a capacitance, and the value of the capacitance being 1 over Cs. Also, this circuit number 2 is being supplied by a current source, and it's a DC current source. So similarly, if you're going to convert that current in S domain, then it must be treated as a unit step, the value of which being 2. So if we now draw our circuit in S domain, then the current here is now 2 over S. We have the parallel combination of the resistance and the capacitance. So the value of R is 10. And the value of your capacitance is 500 milli. So following this format, that must be 1 divided by 500 milli times S. Well, we can simplify that further to be, this is 0.5, I believe. So 1 over 0.5 is 2. So that must be 2 over S. And the problem is asking us to solve for the voltage across the capacitance. So we have to solve for the voltage across the capacitance, which is here. Let me label this V of S. There. Again, good thing about this method is we are actually allowed to apply all the network laws and theorems which we have already discussed or which we have already learned from our previous subjects. So I believe the easiest way for us to be able to determine the voltage across the capacitance is to do a current divider formula because we know the total current entering two branches. We could therefore use current divider formula to solve for the current passing through the capacitance. Let me label that current to be I of S. So let's solve for I of S first. I of S is equal to 2 over S multiplied to the impedance at the other branch, which is 10, divided by the total impedance, which happens to be 10, plus, the sum of impedances rather, 10 plus 2 over S. Simplifying, this becomes 20 over S divided by, at the denominator, we will have a common denominator of S. This becomes 10S plus 2. So numerator is 20 over S, denominator is 10S plus 2 over S. Now, by mathematics, you know that you're going to multiply 20 over S to the reciprocal of this. In short, S gets cancelled and we will be left with a 20 over 10S plus 2. There. We can further simplify this because we will be anticipating that we are supposed to convert this one to t-domain later on. So we can simplify this as early as now by again getting rid of the coefficient of S here. So we can factor out the 10 to give us 20 over 10 multiplied to S plus 0.2. 20 over 10 is 2 divided by S plus 0.2. So there. However, of course, this is not yet our final answer. This is just the current passing through the capacitive branch. Our final answer is the voltage. So what do? We simply multiply that current to the impedance of that branch, which happens to be 2 over S. So let's do that now. The voltage V of S, therefore, is equal to the product of the current 2 over S plus 0.2 multiplied to 2 over S. And this now gives us 4 over S times S plus 0.2. This is not yet our final answer because we have to bring this back to t-domain. So, as you probably already know, again, we have to separate the two linear factors at the denominator. So, S and S plus 0.2 can be separated using partial fraction expansion. So, this becomes A over S plus B over S plus 0.2. Cross multiplying, this leads to an equation 4 is equal to A. Again, S gets cancelled for the first term. A should be multiplied therefore to S plus 0.2 and b multiplied to s, because s plus 0.2 gets cancelled this time. There, creating coefficients. So s left side is 0, right side is a plus b, and constants, left side is 4, right side is 0.2a. So a must be 4 over 0.2, which is 20, and b is the negative of a, so b is negative 20. If we substitute that to our original equation here, a over s plus b over s plus 0.2, that gives us a voltage across our capacitance in S domain to be equal to 20 over S minus 20 over S plus 0.2. And finally, the voltage across the capacitance in time domain is 20 minus 20 e raised to negative 0.2 of t. Yeah, there.